Now suppose that S is given by the parameterization R of u comma v. And let's say that S is already known to be orientable, that is, it has two sides. Okay, but how can we actually find an orientation? How can we find this n function that's here in notation form, which will be needed for computation? So how can we find an orientation n vector arrow? So to help us with this, we're going to draw a picture. That is, we're going to draw this picture just to hopefully help convince you that what we're about to do works in general. It's generally speaking, we won't want to draw a picture, but hopefully this quick exploration will allow you to go, aha, yes, that should work. What we do is, well, let's say here's a surface, and let's say this is like the cheesecloth shown earlier. Let's say this is orientable. Okay, then like at one point x comma y comma z, you actually have well, you're going to have grid curves. So let's say let's draw in a grid curve here in blue, and maybe this is uh, yeah, the grid curve for what happens with a fixed value of v, let's say, and then you also will have a grid curve somewhere else, that goes this way for, let's say, a fixed value of the other variable u. And so then when you compute a partial derivative of r with respect to u, maybe you end up getting this vector that's instantaneously in the same direction as the grid curve, and then if you compute the partial derivative with respect to the other variable v, you're going to get an arrow that's instantaneously pointing in the direction of the other grid curve. And so the thing that we actually want is going to be this vector here that needs to be perpendicular to both the red vector and the blue vector. So what we really want, this vector here, this normal vector, is r sub u cross product r sub v. We learned a long time ago, yeah, that this is how you get something that's perpendicular. We want something that's perpendicular to both vectors, and since ru and rv are instantaneously speaking tangent to the surface, then when you cross these two vectors together, you get something that's perpendicular. Now you might actually want to reverse the orientation. Okay, so you might want to reverse the orientation. And it just depends, if you need outwards versus inwards or whatever. So you might need the vector that points the other direction over here. So then what you would need is negative quantity r sub u cross product r sub v. And you won't know until you draw the picture and so on. So generally speaking, what you need is either the plus or the minus of r sub u cross r sub v. Now, we also note that in the definition we need a unit vector. We need n to be a unit vector. So to get that unit vector, what we'll do is we'll just say that n arrow should be plus or minus. Okay, plus or minus again because we don't know which yet. So we'll have r sub u cross r sub v, and in the denominator what you'll have is the magnitude of r sub u cross r sub v, just to get something that's a unit vector. Here we're normalizing. Now the thing is, this plus or minus sign, I want to say one more thing about it, is that you have to pick one, either the plus sign or the minus sign, based on the orientation you need. Okay, and that's going to all depend on the specific problem and all that. So let's take a look at an example. So question, let capital S be the sphere of radius 7 centered at the origin. So let's take a sphere. Yeah, that is orientable. There's an inside. So if you had like a plastic beach ball or something, there's a part that you can touch. And then there's the other side of the surface that you cannot touch unless you were to somehow be able to invert the beach ball. And what we'll do is we'll just borrow from spherical coordinates. Let's just use u for the phi coordinate and use v for the theta coordinate from spherical coordinates. Then we can parameterize s with the following vector function. So r of u comma v is equal to angle bracket 7 times sine of u times cosine of v, comma 7 times sine of u times sine of v, comma 7 times cosine of u. Then there's some details to work out, but if you do r sub u Cartesian product r sub u cross product r sub v, skipping some of the details of setting up, taking the partial derivatives and writing out the 3/3 determinant and so on and so forth, you'll end up with 49 sine squared u cosine of v, comma 49 sine squared u sine of v, and 49 sine of u cosine of u. So based on this, if you took the magnitude of this vector here, we'll take r sub u cross r sub v, the vector that we just got. If you compute its magnitude, again, this we're not showing all the details for right now, is 49 times sine of u. You got to work out some of these details, and so this means that one orientation of this sphere S is, so n, we'll just specify that n is actually really a function of u and v. So it's going to equal, well, this divided by that. So we end up with the fraction 49 sine squared u cosine v, comma 49 sine squared u sine of v, comma 49 sine of u cosine of u, over 49 sine of u. Now, if we go ahead and cancel what can be canceled, there's a 49 sine of u in all of these, and as well in the denominator. This cleans up to just become actually fairly nice as sine of u cosine of v, comma sine of u sine of v, comma cosine of u. So this is one orientation. Okay, so this answers the question. Okay, another orientation, the other orientation, of S is just with a negative sign in front of this, is just negative vector sine of u cosine of v, comma sine of u sine of v, cosine of u. So it's not automatically that one of these is the outward and one of these is the inward or anything like that. Don't make any assumptions about what the plus or minus sign does. We'll have to figure out, you'd have to figure out, generally speaking, which one's which by drawing just a little bit of a picture. As far as an interactive question goes, though, let's do the following just as a good review of what's going on with spherical coordinates. So let's just ask this interactive question. Ask, look, there are 3 spherical coordinates, aren't there? 3 spherical coordinates. So why did this parameterization involving just 2 parametric variables, u and v, why did this work?